230 million years ago, Earth entered one of the most disruptive climate episodes in its entire geological history. For nearly 2 million years, rainfall intensified across much of the planet, transforming deserts into wetlands, reshaping ecosystems, and permanently altering the course of evolution. This period, known as the Carnian Pluvial Event, was not a brief anomaly or a regional disturbance. It was a global systems failure and reset driven by forces deep within the planet itself. To understand why the Carnian Pluvial Event was so consequential, it is necessary to understand the world that existed before it. For tens of millions of years leading up to the late Triassic, Earth was locked in a state of extreme aridity. After the collapse of the Carboniferous coal forests, the planet entered a prolonged dry phase that left a clear and consistent signature in the geological record. Vast expanses of red desert sediments accumulated across what are now North America, North Africa, Europe, and Asia. Wind-driven sands and oxidized soils built up in layers hundreds of meters thick, indicating a climate dominated by heat, drought, and atmospheric stagnation. This was the age of Pangaea. By around 300 million years ago, nearly all of Earth's land masses had merged into a single supercontinent. Pangaea stretched from pole to pole, forming a colossal land barrier that disrupted ocean circulation and weakened the global water cycle. Moisture evaporated primarily along coastal margins, while the continental interior became so dry that cloud formation was rare. With no large inland seas and weakened monsoon systems, precipitation was minimal and unreliable. Vegetation reflected this harsh reality. The dense moisture-trapping forests of earlier eras were gone. In their place were drought-tolerant gymnosperms, early conifer-like plants, and sparse fern communities clinging to limited water sources. There were no expansive canopies, no rich soils, and no vigorous growth cycles. Life persisted, but it did not flourish. Animal ecosystems were equally constrained. Early archosaurs, the distant ancestors of dinosaurs, birds, and crocodiles, had appeared, but they remained small and ecologically insignificant. Reptile populations were scattered and isolated, limited by food scarcity and environmental stress. Large terrestrial animals struggled to survive prolonged drought, and ecosystems lacked the complexity seen in later periods. In the skies, remnants of an older world still lingered. Giant insects, once dominant during the high-oxygen Carboniferous, had not entirely disappeared, but their size and abundance had declined sharply. Falling oxygen levels removed the physiological advantage that once allowed them to grow to extraordinary proportions. The Triassic world was stable, but it was a fragile stability, one that masked how close the system was to collapse. Geologists studying mid-Triassic rock layers see this clearly today. The sediments tell a story of stagnation, expanding deserts, shrinking waterways, and ecosystems trapped in evolutionary stasis. There was no indication, at least on the surface, that Earth was approaching a dramatic turning point. That turning point began far below the surface. Deep within the mantle beneath what is now Alaska and Western Canada, a massive hotspot began accumulating energy. Magma rose steadily, pressurizing the crust over thousands of years. Around 234 million years ago, the system broke. What followed was the eruption of the Wrangellia Large Igneous Province, one of the most extensive volcanic events of the Mesozoic era. This was not a single catastrophic explosion. It was a prolonged outpouring of lava lasting more than 1 million years. Thousands of cubic kilometers of basalt flooded the surface, burning through organic-rich sediments deposited during earlier periods. As these layers ignited, they released enormous quantities of carbon dioxide and methane that had been locked underground for hundreds of millions of years. The scale of gas release overwhelmed Earth's natural carbon regulation systems. At the time, the planet lacked extensive forests capable of absorbing excess carbon, and ocean circulation was too sluggish to sequester it efficiently. In a geologically short interval, atmospheric carbon dioxide levels rose to more than 1,000 parts per million, more than double modern levels. Global temperatures followed. Average surface temperatures increased by approximately 3 to 4 degrees Celsius. The oceans absorbed much of this heat, warming rapidly and triggering another destabilizing process: the breakdown of methane hydrates. These ice-like compounds, stable only under low temperatures and high pressure, released additional methane into the atmosphere as ocean waters warmed. Methane is far more potent than carbon dioxide as a greenhouse gas. Its release created a feedback loop in which warming caused methane release, and methane release caused further warming. Earth's climate system crossed a threshold. What made this event different from other volcanic catastrophes was not the intensity of the eruptions, but their climatic outcome. Unlike the Siberian traps, which triggered mass extinction through extreme heat and toxicity, Wrangellia fundamentally rewired the water cycle. As greenhouse gases accumulated, the atmosphere's capacity to hold moisture increased dramatically. Warmer oceans evaporated at unprecedented rates. In the supercontinent configuration of Pangaea, this led to the formation of mega-monsoon systems far more powerful than anything seen today. Moist air from the oceans was drawn deep into the continental interior, penetrating hundreds, and in some cases thousands, of kilometers inland. Regions that had been arid for tens of millions of years began receiving sustained rainfall. But this was not continuous rain in the modern sense. It was a series of powerful, recurring precipitation cycles lasting hundreds to thousands of years each. Together, these cycles define the Carnian Pluvial Event. Geological evidence of this transformation appears simultaneously across the globe. In the Dolomites of Italy, layers of red desert sediments are abruptly replaced by organic-rich shales and mudstones deposited by rivers and lakes. Similar patterns appear in China, South America, and North Africa. The synchronization of these layers confirms that the event was global, not regional. Water reshaped the land with renewed force. Rivers expanded, lakes formed, and soils regained fertility. Vegetation responded quickly. Drought-adapted plants declined, while new moisture-loving species spread rapidly. Dense forests returned to regions that had been barren for millions of years, creating complex terrestrial habitats. But this transformation carried a darker consequence. Volcanic gases also included sulfur dioxide, which reacted with atmospheric moisture to produce weak but persistent acid rain. Fossil leaves from the period show characteristic damage consistent with acid exposure, and amber deposits preserve evidence of chemical stress. While rainfall revived ecosystems on land, it placed enormous strain on life in the oceans. Runoff from the continents carried vast quantities of nutrients and organic material into the sea. As algae bloomed and died, their decomposition consumed dissolved oxygen. At the same time, warmer waters held less oxygen overall. The result was widespread oceanic anoxia, zones where oxygen levels dropped too low to support most marine life. In many regions, anoxia progressed into euxinia, a state dominated by anaerobic bacteria that produce hydrogen sulfide, a potent toxin. This chemical shift devastated marine ecosystems. Roughly 30% of marine species disappeared during the Carnian. Conodonts, which had survived for more than 300 million years, were nearly wiped out. Ammonoids and crinoids declined sharply. Organisms with calcium carbonate shells suffered as ocean acidification dissolved their protective structures. On land, not all species could adapt to the new humid world. Many reptiles specialized for dry conditions declined or vanished. Yet within this ecological upheaval, opportunity emerged. The Carnian Pluvial Event opened the door for a group that had previously played only a minor role. The dinosaurs. Before the CPE, dinosaur ancestors were small, marginal components of Triassic ecosystems. The new humid forests, extensive river systems, and abundant plant life favored animals with upright posture, efficient lungs, and advanced thermoregulation. Archosaurs possessed these traits. As herbivorous forms expanded, predators evolved alongside them. One of the earliest true dinosaurs, Herrerasaurus, appears in the fossil record during this window. It was not large by later standards, but its anatomy, lightweight build, powerful hind limbs, and efficient movement represented a decisive evolutionary shift. Trackway evidence tells the story clearly. In regions like the Dolomites, dinosaur footprints were rare before the Carnian Pluvial Event. Immediately afterward, more than 90% of vertebrate tracks belonged to dinosaurs. Within a few million years, they had become ecologically dominant. The configuration of Pangaea amplified this rise. Continuous land corridors allowed dinosaurs to migrate rapidly, spreading across newly habitable regions and diversifying as populations became isolated by geography and climate. When volcanic activity eventually declined, the planet began to rebalance. Carbon dioxide levels fell slowly. Rainfall lessened. A new equilibrium emerged, but the biological hierarchy had changed permanently. The Carnian Pluvial Event was not merely a climate anomaly. It was an evolutionary turning point, a reminder that Earth's internal processes can redefine life itself. It shows how tightly linked geology, atmosphere, oceans, and biology truly are. Looking back, the Carnian stands as both a warning and a lesson. Climate systems have limits. When those limits are crossed, change does not come gently. It arrives in waves, reshaping the world in ways that cannot be undone. 2 million years of rain did not just change the Triassic, they changed everything that followed.